for today. So, today's lecture, we're just about wrapping up the segment on hypothesis testing and statistical significance. And we've shown you a whole lot of concepts, and I want to kind of go over them and do some examples. And then on Friday, you will do a midterm review. So announcements for today, your homework is due tomorrow evening. Don't forget, midterm is this Friday, 7 o'clock Pacific time. We have a bunch of links with some information about logistics, how it's going to work. You're going to take it online. We have a review session recording. We'd encourage you to take the online practice exam. So if there are any logistical issues, you find out at it in advance rather than during the timed setting. And we just want to mention a little bit of advice for those of you, if you're a freshman, if this is your first exam in college. You can do some studying, some refresher. We have a bunch of practice exams. You could take one or two to get yourself familiar with the format, check if there's any topics that are worth doing a little last minute studying on. And then I encourage you to get some good sleep tomorrow evening. Don't pull an all-nighter, don't cram too hard. My experience is that cramming just doesn't really work all that well. You've done a bunch of practice throughout this course, so don't stress about it too much. Don't stress about your grade too much. The purpose of this course is hopefully you learn some stuff, you learn some skills, you learn some stuff that'll be helpful to you in your future life. Almost no one's going to care all that much about your grade in any one class, let alone your grade on any one exam. So I know it's easy for me to say, but I just wanted to put in perspective that it's easy for exam to be really stressful and seem like a huge deal. But 10 years from now, when you're looking back on this, you'll say, oh, I guess it didn't matter to my life that much. So I hope that's a little bit of encouragement. Okay, so hypothesis testing. Do I think the majority of you will pass as long as you've been engaged with the class so far? I hope so. I think so. This is not intended to be a weeder class where we kill you. All right, how to do a hypothesis test. So let me just walk you through the procedure for doing a hypothesis test. First step in any hypothesis test is to figure out what you want to test, okay? And the really helpful way to do that is to write down a null hypothesis and an alternative hypothesis, okay? So if you get a hypothesis testing question, or if you're experiencing this in real life, and you've got some data and it looks like there might be a trend in the data or something, or you're collecting data because you want to test a particular theory, typically the alternative hypothesis is the view of the world that we're hoping might be true, we think might be true, would be interesting if it were true. And the null hypothesis is usually the view of the world that's boring, that says there's nothing happening but just chance, that's not actually a real connection here, it's just the results of randomness. In any case, the null hypothesis has to be a completely specified chance model. That means something where all the probabilities are completely specified so that you can simulate data from it. Typically, the alternative hypothesis does not have that property. So if you're unclear, you can look at these two hypotheses and figure out which one am I able to simulate, and that's the one that has to be your null hypothesis. So a common null hypothesis will say something like, this coin is fair and the outcomes are a result of random flips, or the outcomes of this experiment are solely due to chance, and the chances of each thing happening are such and such. Then next thing you want to do is choose a test statistic. And the test statistic is designed to help you select between these two possibilities, between the null and the alternative. You're going to gather a bunch of data, and you need a single number. We want a single number to help us choose between those two. So the test statistic is something that, given a whole bunch of data, summarizes it in a single number. All right. And for a test statistic to be good, we'd like it to be that larger values of the test statistic are evidence for the alternative, and smaller values are evidence for the null. And the larger the value, the stronger, the more you're inclined to think the alternative is true. And the smaller, the more you're inclined to think the null is true. Or it could be the other way around. That would also be okay. But the important thing is that you need to be able to say one direction favors the null and one direction favors the alternative. How do you choose a test statistic? We gave you some hints in some previous slides. There are a couple common themes. There's no hard and fast rules. If you are comparing two categorical distributions, the total variation distance is often useful. If you're comparing two numerical distributions, often the difference of means is useful. If there's a single quantity you care about, then you might look at something like the average. For instance, how long did people live after getting the treatment? Next step is you compute the value of the test statistic in your observed data. You take the data that was observed from the real world and you can summarize that with a test statistic. And then you make a prediction about what kinds of outcomes you would be likely to get if the null hypothesis were true. So you imagine a hypothetical universe where the null hypothesis is true, and then you run simulations to generate a whole bunch of simulated outcomes that could have happened in that other universe. And for each data set you collect in each simulated universe, you summarize it with a statistic. You gather a bunch of those and you plot them on a histogram, and you check whether the observed value appears to be consistent, that like it could have come from that distribution plausibly without requiring too great a coincidence to believe in that. Often we quantify this by computing a p-value and comparing the p-value to some cutoff, to some threshold. Okay, so what's a p-value? A p-value is a way of summarizing the extent to which the observed statistic is consistent with the null hypothesis, consistent with the predictions made by the null hypothesis, or inconsistent. And it's a quantitative measure. It's a number between 0 and 1, where the smaller it is, the closer it is to 0, the more inconsistent your observed data is with the null. Okay, so we have a formal definition, which we've shown you before. It's the probability that in a universe where the null hypothesis is true, probability that in that universe you would observe a test statistic that's equal to the observed value, or even more extreme, even further in the direction of the alternative hypothesis. So that's a super, super mouthful. Okay, so what are we saying here? We're saying we're going to make a decision. We're going to make a decision between the null and the alternative. And a reasonable way to do that is to pick some kind of a threshold. And if the statistic is above that threshold, then we're going to decide I'm going with the alternative. And if it's below that, we're going to decide I'm going with the null. All right. So if you have a threshold in mind, you say if values of the statistic are above 100, I'm going with the alternative. Then we can ask the question of how likely is it, if the null actually was true, to get a value of the statistic that's above 100? And let's say that's 1 in a million. All right, then we'd be entitled to say, wow, it's really unlikely that you'll get a value of 100 or larger if the null were true. So if you actually see the value 100 or any larger value, that seems unlikely to have come from the null. You would have to believe that there was a 1 in a million coincidence that happened for you to believe that this data came from the null, the distribution that arises out of the null hypothesis. Okay, so the p-value is a way of quantifying that number 1 in a million. All right, so maybe you've heard of the notion of like a 1 in 10-year flood, or 1 in 20-year flood, or 1 in 100-year flood. That's kind of a way of quantifying how unusual is a flood. If you see a 1 in 10-year flood, that's a pretty unusual flood. The chances that you see floodwaters get that high in any particular year are only about 1 out of 10. And a 1 in 100 year, that's really unusual for the waters to get that high. The chances the water gets that high in any given year is only 1 out of 100. So if you saw waters that were way above the 1 in 1,000 year mark, you'd be saying, whoa, that seems really unlikely. Or in other words, we might not design buildings to deal with that because that seems like too much of a coincidence. So the p-value is the same thing. It's like that 1 in 10 or 1 in 100 or 1 in 1,000, except now instead of dealing with floods, it's dealing with how much of a coincidence you have to believe in to believe that the observed data came from the null hypothesis. So it's a way of quantifying how inconsistent the observed data is with the null. Okay, so the smaller the p-value is, we're going to say that's kind of, in some sense, more evidence against the null hypothesis. Now, to make our final decision, we're going to have a cutoff. All right, so typical cutoff would be 0.05. All right. So if the p-value is below 0.05, we might say, I no longer believe in the null hypothesis. I'm rejecting the null hypothesis. This is a statistically significant result. That 0.05 is a completely arbitrary cutoff. It's a common convention. We'll tell you what cutoff to use. In most scientific papers, if a cutoff is not specified, the conventional answer is 0.05. But some papers will use something different. Some will use 0.01. In physics, they use something even more extreme. I forget, I think it's about 0.001. Maybe it's 0.0001, because they really don't want to have a situation where they announce they've discovered a new particle and it shows up in newspaper headlines, and then 3 years later they say, oops, no, actually it wasn't real. Okay. So here's one of the things you need to get comfortable with hypothesis testing. Hypothesis testing, we've got some data. We're trying to make a decision. Do I go with a view of the world that says the null hypothesis is true, or do I go with alternative hypothesis? The thing you got to get comfortable with is you can be wrong. You're never going to know whether your decision was right. Okay, so we're making the best decision we can with the information available, but we still might be wrong. So, for instance, let's say the null hypothesis is true. We're hoping that if you run a hypothesis test, then you'll end up with a result that doesn't reject the null hypothesis. And if so, that's good. You made the right decision. But it's possible, it could happen by chance, that you get a random sample of data that's just unusual. And when you compute the test statistic, you end up with something that's below the p-value cutoff, and you decide, I'm rejecting the null hypothesis. This favors the alternative. That could happen. And if it happens, you've made a wrong decision because actually the null was true, but you decided to reject the null. This can happen in real life, okay? And the other way around can happen too. It could be that the alternative is true, but we fail to reject the null hypothesis. We think that the null hypothesis still could be true. Both of these happen in real life. You have medical trials that detect what looks like a useful correlation. It looks like this drug is useful, but then you do more trials and you later discover, no, it actually wasn't. It was just, we happened to get a random sample that was unusual. So there's always the chance of error here. So let's try to quantify the chance of error. And I want to have you think through this. I'm going to have you take a first stab at this. So there's about 1,500 of you in data 8, a little less than that. And let's say each one of you gets assigned a homework assignment. Man, this would be cruel. Your next homework assignment is you have to toss a coin 2,000 times. Oh, man. And then you have to count the number of heads. You compute the absolute value of the difference between that and 1,000. Use that as your test statistic. Use a hypothesis test to test the null hypothesis that the coin is fair against the alternative that the coin is not. You compute the p-value. You use a 5% cutoff. If your p-value is below 0.05, then you reject the null hypothesis. And suppose that all 1,500 of you are using coins that actually are fair. So now my question to you is, how many of you are gonna wrongly conclude that your coin was unfair? How many of you are going to wrongly reject the null? Yeah. Yeah. Yeah, I like your answers. Yeah. Yeah. 5%. 5%. Yeah, I like your answers. That crow really wanted to have a word too. My new teaching assistants. Yeah. So what's going on? Why 5%? Well, let's look at what distribution of the values of this test statistic you get if the coin is fair. It'll look something like this. We did a simulation and plotted this for you, and it's going to look something like this. And you're going to choose a cutoff that says if the p-value is less than 0.05, then reject the null. Well, where does that correspond to in this graph? It corresponds to a yellow line where the area to the right of that is 0.05. All right. So if you have an observed outcome that's to the right of the yellow line, then you'll compute a p-value that's less than 0.05. And if you have an outcome that's to the left of the yellow line, then you'll have a p-value that's bigger than 0.05. Remember, the yellow line is where the cutoff, what corresponds to a p-value of 0.05. So if you get an outcome that's larger than the yellow thing, you reject the null, and that happens 5% of the time. That was just how we defined p-value and cutoff. All right. So it's just like saying, how often are you going to get a 1 in 20 year flood? The answer is every 1 in 20 years. How often are you going to wrongly reject the null if you use a 5% cutoff? 5% of the time. Okay. Saw a few questions in chat. Why did I use this particular test statistic? Because the alternative said the coin was not fair. Might have been biased towards heads, might have been biased towards tails. So we wanted a test statistic where larger values favor the alternative. If I hadn't done the absolute value, then I get into trouble. Flip the coin 2,000 times. If I got 1,500 heads, I'm suspicious it's not fair. If I got 500 heads, I'm suspicious, equally suspicious it's not fair. So really what I care about is the difference between 1,000, and I don't care about the sign, whether that's above 1,000 or below 1,000. The test statistic was minus 1,000 because 1,000 is the number you would get if the coin was fair. All right, so if the coin's fair, 1,000 out of the 2,000 flips are going to be heads. If I get 1,100, that's sort of equally suspicious as 900. All right. In this particular test statistic, which I chose it so that larger values favor the alternative, that's kind of convenient for a lot of reasons. It doesn't have to be. It could be the other way around. If the alternative hypothesis had a direction, like the alternative hypothesis said heads are more likely, then I would not have used the absolute value. I might have just used the number of heads out of 2,000, because larger values would favor the alternative hypothesis that heads are more likely, and smaller values would favor the null. It's a little confusing, but if I've somehow narrowed things down to think that the only two possibilities is that the coin is fair or it's biased towards heads, like maybe we're in a betting game and you win $1 every time you get a heads, and I'm looking at your coin, I'm thinking you might be motivated to cheat, but only by making it biased towards heads. Say I've only narrowed it down to the only two possibilities, and you flip the coin 2,000 times and you get 800 heads, less than the 1,000 I would have kind of naively expected if it was fair, then I think it's more likely that you had a fair coin than you had a coin that was biased towards heads. Okay. All right. So what the takeaway from this is that this cutoff, this 5% cutoff for the p-value, it's an error probability. It's the probability you make a particular kind of error. If your cutoff is 5%, then and your null hypothesis happens to be true, then it's the probability that you falsely reject the null hypothesis. Okay, so choosing the cutoff is a way of choosing the chances of making a particular kind of mistake. Like if I'm testing a drug and I choose a 5% cutoff, that's the chances that if the drug is actually useless, that I conclude that it's good. Okay, so if I'm testing lots and lots and lots of different drugs and they all turn out to be useless, I don't realize that, but they are all useless, then only 5%, exactly 5% of those drugs in those tests will look like the drugs are good. I'll reject the null and I'll favor the alternative. Okay. Now, if the alternative is actually true, then I can't tell you what the error probability is going to be, because that depends on like the sample size and so on. Suppose your coin is actually biased. The true probability of heads is 100%. It's got heads on both sides. Then I think I'm very likely to catch that with a hypothesis test, as long as you have a reasonable sample size. On the other hand, if the alternative was true, your coin is not fair, and the actual heads probability of your coin was 0.5001 instead of 0.5, you would need to flip that coin a ridiculously large number of times before I would have any chance of detecting that. So the other kind of error, that the alternative is true and I don't reject the null, is not so easy to control. It's more complicated. It's not set by just the cutoff value. Okay, so the cutoff is something that doesn't depend on the observed data. We decide on it before we look at the results. It's a way of controlling the chances that we make a particular kind of error. The p-value depends on the observed data. It's a way of summarizing how consistent or inconsistent the observed data is with the null hypothesis. Okay, so now I want to do some examples. I want to do some examples of hypothesis testing. And here's a nice one with Benford's law. So Benford's law makes a prediction about the distribution of values of the first digit of numbers if you have numbers that are randomly chosen from a very large range. And it suggests that it'll have a particular distribution. And I want to show you what that distribution looks like. It looks like something like this. If you have numbers from a very large range that span many orders of magnitude, then it's much more likely that the first number, the first digit of a randomly chosen number will be 1 than it'll be 9. Okay, this is Benford's law is a idea that's been used in a variety of contexts. For instance, it's been used for detecting fraud in tax returns. If people are faking the numbers on their tax return, well, if they're reporting numbers on their tax return honestly, then it's likely to follow Benford's law. But if they're faking the numbers on their tax return and just writing in arbitrary numbers, then humans, don't necessarily aren't very good at picking random numbers. And so the numbers they pick don't necessarily follow this distribution. And so it's been successfully used to identify potentially fraudulent tax returns, where you check the distribution of the first digit of the numbers in a tax return. And if it doesn't approximately follow this distribution, then we do an audit of you. Doesn't necessarily mean you were cheating, but it's suspicious. All right, Benford's law is not going to be on the midterm, but this is an example of using hypothesis testing. So I want to walk you through this example. I think it's kind of fun. All right, so we've written some code for you that will, given a number, will compute the first digit of that number. For instance, if you have 32, the first digit of that number is a 3, and the first digit of this number is a 1. And we're going to apply that to some data of counties across the US, all the counties in the US and their population. So not looking at tax returns because I didn't have a big collection of tax returns to use in my data set. So we're looking at county populations. And so these numbers span a large range. Some counties are very small, some are very large. Okay, so let's look at the distribution of the first digit of these population numbers in this table. So we're going to do that by calling apply. We're going to take these population numbers and apply this first digit function. That will give me a new array, and I'm going to stick that in a new column. And so this shows me just the first digit of the population. All right. And we had a little over 3,100 counties. And now I'm going to compare the distribution of those first digits from this data set compared to what Benford's law would predict. Okay. So in blue are the numbers, the observed numbers that we got from this data set of counties. Let's say I wanted to test whether these numbers are real or whether someone was just making up numbers to avoid collecting the data. And the yellow is what Benford's law would predict, the distribution. So just visually looking at that, looks pretty similar, but not identical. So you might ask, okay, those differences between the bars, is that a large difference or is it a small difference? In particular, is this the kind of difference that you'd expect to see just by chance? I mean, just by chance, you wouldn't expect the blue numbers to be exactly equal to the blue bars. There'll be a little bit of variation just as a result of random chance, but how much exactly? So we're going to use a hypothesis test to quantify that. So yeah, today's lecture is an example of hypothesis testing. These are examples of hypothesis tests. Hypothesis tests are in scope. Benford's law is not what I want you to learn. I want you to learn how to do a hypothesis test. So in particular, the relevant idea here is we have some theory about how we think the data is distributed. And we're going to try to test that. So Benford had a theory. He said, here's how I predict the data should be distributed. We're going to test whether the data actually is distributed that way. All right, so I want you to think about how we would use a hypothesis test to test whether this data is distributed according to Benford's law. What would remember the first step in a hypothesis test is to write down a null and an alternative hypothesis. What would you list as your null hypothesis? Yeah, good stuff. The distribution of the first digit of the population data follows Benford's law, and any deviation from that is due to random chance. That'd be a great null hypothesis. Love it. Okay, alternative hypothesis would be not that. The opposite of the null, that the distribution of the first digit of the population data in our county's data set does not follow Benford's law. Okay, so those are our two hypotheses. Now we want to identify a test statistic. Can anyone suggest what kind of test statistic would be appropriate here? Very good, very good. Okay, I like TVD. I like TVD because in some senses it's categorical. We have these 9 categories for the 9 first digits. And whenever you're looking at the whether 2 categorical distributions to see how similar they are, the TVD, the total variation distance, is a very good way to measure how similar or dissimilar they are. Okay, great. Now, help me out with the next one. Which values of the test statistic favor the alternative hypothesis? So let me write down the null to help you with that. Yeah, bigger values, because the more that the observed data differs from Benford's law, that will cause a larger value of the TVD, and so a larger value of the TVD would make you think the alternative, that it's not following Benford's law. Okay, all right, very good. Very good. So let's go implement this. Let's first compute the observed value of the test statistic. So we're going to use the TVD as our test statistic. And to compute that, the way you compute that is you take the difference between the observed proportions and what Benford's law predicts. And then we take the absolute value of those differences, and then we sum that up and you divide by 2 because the TVD says divide by 2 to get a number between 0 to 1. And if I did that right, we should get a TVD. And so there's our TVD, the TVD between the yellow and the blue bars. That's the test statistic for the observed data. Now let's figure out, the next step is to figure out how to make a prediction. We got to predict what values of the TVD of the test statistic we're likely to see if Benford's law, if the null hypothesis was true, if the data did follow, was generated according to Benford's law. Okay, so we're going to imagine a hypothetical universe where someone is generating population data in a way that follows the null hypothesis. In other words, in a way that follows Benford's law. And we're going to simulate some data sets that we could get in that universe. And we're going to try to compute their test statistics. So what does Benford's law say about how the distribution of the first digits will be? Well, it tells us what the distribution is. So if we want to imagine that we've generated about 3,100 population numbers following that rule and took in their first digits, we can simulate that by using sample proportions. So we're going to choose num counties different numbers and different digits, and each digit is going to follow the distribution given by Benford's law. And so, for instance, we could run that, and here would be the proportions that you would get out of a random sample chosen in this way. Here would be one example you could get from one such simulation. In this simulation, 29.5% of the numbers started with a 1, 17.3% started with a 2, and so on. And I could do it again with another simulation, and there's another simulated data set. And then I would need to compute the TVD of that. That's easy. So that's what we're going to do next in our simulation, is we're going to do one simulation and summarize that with a single number, the test statistic. So let's write some code to do that. Well, we already discovered how to compute the TVD. So do this, except we use, instead of the observed data, we use the simulated data. And there we did a simulation, and we got a TVD in our simulation of 0.021. All right, num counties is the number of counties in our data set. It's the number of rows in this table. I filled it in like this. There were a little over 3,100 counties in the US. So I'm imagining a hypothetical universe where these numbers gets filled in. Well, basically the first digit gets filled in by doing a random draw from Benford's law from this distribution. Okay, so instead of getting actual population data, we're imagining drawing digits from this distribution and filling in, you know, a new fake table with those simulated digits. Okay, I'm going to want to do this many times. That was one simulation, so let me put that in a function. And I'm going to have this simulation return the TVD. So now it's in a function, and I can simulate, do a simulated experiment, simulate under the assumption the null hypothesis is true, and it tells me the TVD. And I can repeat that many times, and you can see what the TVDs look like. Well, I'm getting TVDs like 0.01, 0.02, 0.01-ish, 0.02-ish. So that gives me an idea of the range of values that of TVD values that I would be likely to get if the null were true. So to make this more systematic, what we're going to do is we're going to simulate many times, and we're going to draw a histogram of the distribution of these values of the TVD. And you know the code for how to do this. We're going to put all those values in an array. We use a for loop to repeat many times. Let's repeat 10,000 times, because it's a computer and it can do a lot for us really fast. And in each iteration, we're going to do one simulation and append the result to this array. And let's see if I typoed this. Okay. All right, so we're running the code. And now let's display this. Histogram. And there's a histogram of the TVDs that we get out of our simulation, assuming the null hypothesis is true. So these are the values of the distribution of the values of the test statistic that you'd expect to see if the null hypothesis was true. So now we can compare the observed value of the TVD. The observed value was 0.019. So where is that on this histogram? It's right about here. So what would you say? Do you think this is the observed data is consistent with the predictions made by the null, or inconsistent? Yeah, consistent. It's kind of in the middle of this distribution. It's in the middle of values that you would expect to get, the range of values you would expect to get if the null were true. It would be a perfectly reasonable, plausible value you could get if the null were true. Not at all unusual, doesn't require believing in some extreme coincidence, not suspicious in any way. Okay, so the data that we're observing in this case looks entirely consistent with Benford's law. We can quantify that by computing a p-value. And the way we compute a p-value is we're going to look at how many simulated TVDs are at least this. Y greater than or equal to? Why did I say at least? Why greater than or equal to and not less than or equal to? Because large values support the alternative. Yeah, yeah, yeah. So it's like, imagine before you saw the observed data, you did this simulation first, and you said, here's the range of values that I expect to see, and let me figure out before I even get any observed data or look at the observed data, what am I going to consider so outlandish that it seems unlikely to have happened from the null hypothesis? Well, it must be values on the right-hand side of this histogram, larger values, because larger values support the alternative. So there's going to be some threshold here where if the observed value is larger than that, then I'm going to say, wow, that was so unlikely to have come out of the null distribution that I'm going to reject the null. Okay, so what we care about is the right-hand tail of this distribution. And the reason we care about looking at all the simulations that gave a value that was at least 0.019 or larger than 0.019 is because any value that's bigger than 0.019 is even more unlikely to happen from the null. It's even more supportive of the alternative. So if 0.019 is going to make you reject the null, then bigger values ought to make you reject the null too. All right, so we're looking at, if we reject 0.019, we're going to reject everything bigger than that. So how much area is that of those areas that we're contemplating rejecting? And if that area was less than 5%, then I'd say, okay, yeah, go ahead and reject. That's a kind of a less than 5% coincidence. But in this case, it's 44%. So don't reject the null. you know, it's entirely plausible you could get this value coming out of the null. Okay, so final answer, you tell me, is the data consistent with the null hypothesis? Yes, it is. I didn't even tell you what the p-value cutoff was, because any reasonable p-value cutoff, this p-value is not below the cutoff. Like if you use p-value cutoff of 5%, this p-value is not below the cutoff. So you shouldn't reject the null. The data is consistent with the null. Okay. Let's do another example. Oh, great question. Do I accept the alternative? Well, I didn't. No, I don't accept the alternative because the data is consistent with the null. The null hypothesis still looks like it could be true. So I have no particular reason to believe the null is wrong. So therefore, I can't really conclude the alternative is true. I don't reject the alternative. The alternative could be true too. They both, both remain possibilities. Both the null and the alternative remain possibilities. So all I can say is there's no evidence that this stuff deviates from Benford's law. All right. So fail to reject the null. Yep. Either the null or the alternative could still be true. I haven't ruled either one out. All right. Let's do another example. I want to do an example of one more hypothesis test. And this time we're going to work with your data. At the start of the semester, we asked you a couple of survey questions about things like your sleeping habits and how many hours you sleep and what side you sleep on. And so I want to look at what position people in this class sleep on and how many hours of sleep they get. All right. So in this data set, there were like 4 options we gave you for how you sleep: left side, right side, stomach, back. And let's just compare side sleepers to non-side sleepers. All right. So the way I'm going to do that is all the side sleepers, I'm going to create a new column and label them side. And the rest, I'm going to label them back or stomach. So I do that with a function and then I apply. And then I keep only the result of the apply. And now I get a new table that has all of the students who responded to this survey with either whether they're a side sleeper or not and the number of hours that they reported sleeping. Okay, so now let's start by getting a sense of this data. So I did a group here and to look at the average numbers of hours slept. And side sleepers reported sleeping 7.2 hours on average, and non-side sleepers reported sleeping 7.1 hours on average. Would you say that there's an association among data 8 students between sleeping position and numbers of hours of sleep? No association. Okay, how come? Values are not different enough? Similar? So why does similar make you think there's no association? Oh, interesting. I'm starting to see some statements now that are a little different. Maybe there's a weak association. Maybe it's a small association, a small correlation. There's a little bit of relationship. It's just not very strong. Ah, yeah. Okay. So those of you who don't believe there's an association, tell me what you think is going on. Why do you think there's a difference? I mean, there is a difference, even though it's a small one, 7.2 versus 7.1. If you don't think it's an association, yeah, random chance. Okay. All right. Okay. Good. So I would have been really tempted to say, yeah, there's an association because there's a difference, but I don't know whether that's real or not. But I also really understand this is really tempted to say not an association because it's really small and maybe it's just random chance. And it's hard to say. It's hard to say, isn't it? All right. Confounding variables don't enter into this because for an association, you can still have an association even if there's confounding variables. Confounding variables enter into things when you talk about causality. Like if I was going to ask you, does sleep on your slide cause you to sleep longer? But let's not get there. Let's just look at association. So to figure out if there's an association, we actually don't really have enough information to know for sure. So I'm perfectly sympathetic for both those of you who said no and those of you who said yes, but it's weak, and also those of you who said who don't know. Because it's possible there's an association. It's also possible this is just random chance variation. So to figure out whether this could be random chance variation, what we're going to use is a hypothesis test. Okay, so to find out whether there is an association, we're going to use a hypothesis test. So where do we start when we do a hypothesis test? We got to write down a null hypothesis and an alternative hypothesis. So tell you what, you give me the null and I'll give you the alternative. What would you do as a null? No association is your null. Okay. I'm hoping you'll state it in a way that makes it clear what the chance model is, makes it clear how to simulate this. So be a little more specific. Like tell me about what the distribution is, or what the distribution the data comes from is, or something. Yeah, good. I like some of the stuff I'm seeing. The distribution of numbers of hours slept by side sleepers is the same as the distribution of the number of hours slept by everyone else. That would be the null hypothesis. And the alternative hypothesis would say they're not the same. Side sleepers sleep more on average than non-side sleepers. All right. Now let me ask you, would you be better off using an A/B test or a regular hypothesis test to check these hypotheses? Great, A/B test. All right, we're in the same page. An A/B test because we kind of have two samples. We have all the data from the side sleepers and all the data from the non-side sleepers, and we want to compare their distribution. So we want to use an A/B test. Now, what test statistic would be appropriate for testing these null and alternative hypotheses? Sample mean, but the mean of what? Difference in means. Yeah, we would look at the average numbers of sleep for side sleepers minus the average numbers of sleep for non-side sleepers. So great, the difference in means. And so like the 7.2 minus 7.1. All right, so a test statistic, we're going to use the difference in means. The way we're going to do that is if you have a table of data, we're going to group it like this. We're going to get these averages, and then we're going to subtract the 7.2 minus the 7.1, except that if the data was different, then it might not be 7.2, it might be 7.1. All right, so now let's just kind of go through, and I'm going to quickly go through doing the code. We compute the observed test statistic. That's the next step. Using that function we just wrote, and the observed test statistic is 0.1, which makes sense. 7.2 minus 7.1. Side sleepers slept about 0.1 hours longer in our data set, in the observed data set. Now in an A/B test, we're going to simulate. We need to simulate new data under the assumption that the distribution doesn't matter whether you're a side sleeper or not. So we got to get new data. Now, that doesn't really tell us what the distribution of numbers of hours slept is. So how are we going to simulate from this? I'd like to simulate new data, but I don't know what distribution of numbers of hours slept is. So what I'm going to use as my distribution for numbers of hours slept is the hours you reported, the distribution of the hours you reported. All right, so I am going to reshuffle around all your data, where I'm going to randomly label you with not the label you reported, side sleeper or not, but with a randomly chosen, randomly shuffled labels. And if the numbers of hours you sleep is not associated with and not affected by how you sleep, then that relabeling shouldn't affect any of the distribution. That should also be a perfectly valid possible outcome if the null hypothesis is true. All right, so here's how we're going to do that. We're going to shuffle the labels, and that gives me a way to simulate under the null, simulate new data that could have occurred if the null is true. If the null is false, this is a totally bogus way to simulate, because then the labels are connected to the numbers of hours slept, and you can't just shuffle around the labels. But if the labels are unconnected and independent, then sure, go for it. Now we simulate 1,000 samples in this way. You can compute the test statistic for each of those 1,000 samples. And then we're going to visualize the values of the test statistic we get from the simulated data that's simulated assuming the null hypothesis is true. And while my computer computes, then what we're going to do is we're going to look where the observed test statistic falls on this distribution and then see if it looks like it's something that could plausibly have come from this particular distribution on the test statistic. Now, while it's computing, let me answer a few questions. Why did I put with replacement equals true? Because that reorders the labels, giving you exactly the same number of side sleepers and non-side sleepers. So keeping that the same in our simulated data set. That's how A/B testing is done. Can you shuffle either column? Yes, you can shuffle either column. Either way, it will have the same effect. You choose. It's roughly equivalent. All right, there's the distribution of test statistics you would expect to see if the null hypothesis is true. You can see most of them are between -0.1 and 0.1. So just visually, it looks like the actual observed value, 0.1, is sort of plausibly within this range, but we better quantify that because it's a little bit not quite clear cut. You know, maybe you could say this 0.1 is kind of out here in the extreme, or maybe you could say it's still plausibly something that could happen. So we quantify this to make it more precise in these kind of borderline cases by computing the p-value. Now, I just did a computation here, computed how many of the simulated test statistics are less than the observed thing, 0.102. What does that mean the p-value is? What's the p-value? Leave me a message in chat. What's the p-value? Yeah, 1 minus that. Because the alternative hypothesis says this difference is bigger. So larger values favor the alternative. So we care about values that are 0.102 or bigger. All right, so there's about 0.045 fraction of values are bigger. So the p-value is about 0.045. So assuming we use a 5% cutoff, is the data that we got from this class consistent with the null hypothesis? No, you're correct. The p-value is below the cutoff. P-value of 0.045, cutoff 0.05. P-value is below the cutoff. Reject the null. With a 5% cutoff, this data is not consistent with the null hypothesis. This is statistically significant difference. So I think you would be entitled to conclude, it would be reasonable to conclude that the data you were reporting shows an association between side sleeping versus not and numbers of hours of sleep. Okay, so that's how you could use a hypothesis test to check whether there's an association in your data or whether what you're seeing could be due to just random chance. Thank you, everyone. And study hard for the midterm, but not too hard. We'll have a review session and lecture on Friday. See you Friday.